Ground rods buried vertically are more effective than those buried horizontally. This is because vertically oriented ground rods intercept more soil volume, providing a larger surface area for grounding current to dissipate. Soil moisture tends to move vertically, which enhances the conductivity of the grounding electrode. It is generally recommended to install ground rods vertically, but if the trench is sufficiently deep, such as 5 feet, you could consider placing some rods horizontally to maximize surface area contact with the soil. A PVC gas line, identified by its yellow color, should be buried at least 12 inches deeper than the ground rods to maintain separation. It should also be encased in conduit for protection. The 1/2-inch high-density polyethylene conduit is suitable for both electrical and gas lines. However, it is recommended to install both lines in separate trenches to avoid potential interference. When installing ground rods, adhere to specific guidelines to ensure effectiveness and safety. Firstly, install a minimum of 3 ground rods, spaced at least 6 feet apart. Secondly, drive the ground rods to a depth of at least 8 feet. Thirdly, use a copper bonding strap to connect the ground rods together. Fourthly, connect the bonding strap to the electrical service panel. Fifthly, ensure that the minimum grounding resistance is 25 ohms or less. Grounding is a critical aspect of electrical safety and system performance. The purpose of grounding is to provide a low impedance path for fault current to return to the source, allowing overcurrent protective devices, such as circuit breakers or fuses, to quickly clear the fault. This minimizes the risk of electrical shock and equipment damage. Grounding also helps to stabilize voltage levels and reduce electrical noise. When considering grounding methods, it's important to understand the role of ground rods. A ground rod is a conductive rod, typically made of copper or copper-clad steel that is driven into the earth to provide a connection to ground. The effectiveness of a ground rod depends on several factors, including the soil resistivity, the depth of the rod, and the surface area of the rod in contact with the soil. Soil resistivity is a measure of how well the soil conducts electricity. Low soil resistivity is desirable for effective grounding because it allows current to flow more easily from the ground rod into the earth. Soil resistivity varies depending on factors such as moisture content, temperature, and mineral composition. In general, clay soils have lower resistivity than sandy soils. The depth of the ground rod also affects its effectiveness. Deeper ground rods typically have lower resistance to ground because they reach more conductive layers of soil. The National Electrical Code, or NEC, recommends driving ground rods to a depth of at least 8 feet. The surface area of the ground rod in contact with the soil is another important factor. A larger surface area allows for more current to flow from the ground rod into the earth. Vertically oriented ground rods are generally more effective than horizontally oriented ground rods because they intercept more soil volume and have a larger surface area in contact with the soil. Soil moisture also tends to move vertically, which enhances the conductivity of the grounding electrode. In situations where it is difficult to drive ground rods to a depth of 8 feet, such as when encountering bedrock or underground utilities, it may be necessary to use multiple ground rods or other grounding methods. The NEC allows for the use of multiple ground rods, spaced at least 6 feet apart, to reduce the overall resistance to ground. Another option is to use a ground plate or a ground grid, which provides a larger surface area in contact with the soil. When installing ground rods, it is important to follow the manufacturer's instructions and all applicable electrical codes. The ground rod should be driven into undisturbed soil, away from any underground utilities. The top of the ground rod should be flush with the ground or slightly below the surface to prevent it from being damaged. The ground rod should be connected to the electrical system using a copper bonding strap or wire. The bonding strap or wire should be sized according to the NEC. The connection between the ground rod and the bonding strap or wire should be made using a listed connector. The grounding resistance should be tested to ensure that it is within acceptable limits. The NEC requires a grounding resistance of 25 ohms or less. If the grounding resistance is higher than 25 ohms, additional ground rods may be required. In addition to ground rods, other grounding methods can be used to improve the effectiveness of the grounding system. One option is to use a chemical ground rod, which contains a chemical compound that leaches into the surrounding soil, reducing its resistivity. Chemical ground rods are typically used in areas with high soil resistivity. Another option is to use a concrete encased electrode, which consists of a length of bare copper conductor encased in concrete. Concrete encased electrodes are typically used in new construction. When installing a gas line near electrical grounding components, it is important to maintain proper separation to prevent potential hazards. The gas line should be buried at least 12 inches deeper than the ground rods to prevent accidental contact during excavation. The gas line should also be encased in conduit for protection. The conduit should be made of a non-conductive material such as polyvinyl chloride. The gas line should be installed in a separate trench from the electrical grounding components to prevent potential interference. The type of conduit used for electrical and gas lines is also important. High-density polyethylene conduit is a suitable option for both electrical and gas lines. However, it is important to ensure that the conduit is properly sized for the application. The conduit should be large enough to accommodate the wires or pipes that will be installed inside it. The conduit should also be rated for the appropriate voltage and temperature. When installing underground electrical service, it is important to follow all applicable electrical codes and safety standards. The service entrance conductors should be properly sized for the load. The service entrance conductors should be protected from damage. The service entrance conductors should be grounded. The grounding system should be tested to ensure that it is effective. In the specific scenario, where a trench has been excavated to a depth of 5 feet, it may be beneficial to consider placing some ground rods horizontally to maximize surface area contact with the soil. However, it is important to ensure that the ground rods are properly spaced and that the grounding resistance is within acceptable limits. It is also important to maintain proper separation between the ground rods and the gas line. In conclusion, while vertically oriented ground rods are generally more effective, it may be beneficial to utilize both vertical and horizontal rods in a deep trench to maximize grounding effectiveness. Follow the installation guidelines carefully and maintain proper separation between the ground rods, gas line, and conduit. Always consult with a qualified electrician or engineer to ensure that the grounding system is properly designed and installed. The effectiveness of a grounding system is influenced by several key factors, each contributing to its overall performance and safety. Understanding these factors is crucial for designing and installing a grounding system that meets the specific needs of a particular application. Firstly, soil resistivity is a primary determinant of grounding effectiveness. Soil resistivity is a measure of how well the soil conducts electricity, and it varies significantly depending on the soil type, moisture content, temperature, and mineral composition. Low soil resistivity is desirable because it allows current to flow more easily from the grounding electrode into the earth. In areas with high soil resistivity, it may be necessary to use special techniques such as chemical ground rods or ground enhancing compounds to reduce the soil resistivity and improve grounding effectiveness. Secondly, the size and type of grounding electrode play a significant role. Grounding electrodes come in various forms, including ground rods, ground plates, and ground grids. The size and type of grounding electrode should be selected based on the specific application and the soil conditions. Ground rods are typically used for residential and commercial applications, while ground plates and ground grids are used for larger installations such as substations and industrial facilities. The material of the grounding electrode is also important. Copper and copper-clad steel are commonly used because of their excellent conductivity and corrosion resistance. Thirdly, the depth and spacing of grounding electrodes are critical factors. The depth to which a grounding electrode is driven into the earth affects its resistance to ground. Deeper grounding electrodes typically have lower resistance because they reach more conductive layers of soil. The National Electrical Code, or NEC, requires ground rods to be driven to a depth of at least 8 feet. The spacing between grounding electrodes is also important. Multiple grounding electrodes should be spaced at least 6 feet apart to avoid overlapping zones of influence. Fourthly, the connection between the grounding electrode and the electrical system must be secure and reliable. The grounding electrode should be connected to the electrical system using a copper bonding strap or wire. The bonding strap or wire should be sized according to the NEC. The connection between the grounding electrode and the bonding strap or wire should be made using a listed connector. The connection should be protected from corrosion and mechanical damage. Fifthly, the overall grounding system design should consider the specific requirements of the electrical system being grounded. The grounding system should be designed to provide a low impedance path for fault current to return to the source, allowing overcurrent protective devices to quickly clear the fault. The grounding system should also be designed to minimize voltage gradients and reduce the risk of electrical shock. Sixthly, regular testing and maintenance of the grounding system are essential to ensure its continued effectiveness. The grounding resistance should be tested periodically to verify that it is within acceptable limits. The connections between the grounding electrodes and the electrical system should be inspected for corrosion and damage. Any necessary repairs or replacement should be made promptly. When installing underground utilities such as electrical service and gas lines, it is important to follow specific guidelines to ensure safety and prevent potential hazards. The National Fuel Gas Code, or NFGC, specifies requirements for the installation of gas lines. The NEC specifies requirements for the installation of electrical service. The two codes should be followed in conjunction. Firstly, underground utilities should be located and marked before any excavation begins. This can be done by calling the local One Call Center. The One Call Center will notify the utility companies, who will mark the location of the underground utilities. Secondly, excavation should be performed carefully to avoid damaging underground utilities. Hand digging may be necessary in the vicinity of underground utilities. Thirdly, underground utilities should be installed at the proper depth. The depth of burial depends on the type of utility and the location. The NFGC specifies the minimum depth of burial for gas lines. The NEC specifies the minimum depth of burial for electrical service. Fourthly, underground utilities should be protected from damage. Gas lines should be encased in conduit or otherwise protected from mechanical damage. Electrical service conductors should be installed in conduit. Fifthly, underground utilities should be properly grounded and bonded. Gas lines should be bonded to the electrical grounding system. Electrical service conductors should be grounded according to the NEC. Sixthly, underground utilities should be inspected before backfilling. The inspection should verify that the utilities are properly installed and protected. The inspection should also verify that the utilities are properly grounded and bonded. When installing a gas line near electrical grounding components, it is important to maintain proper separation to prevent potential hazards. The gas line should be buried at least 12 inches deeper than the ground rods to prevent accidental contact during excavation. The gas line should also be encased in conduit for protection. The conduit should be made of a non-conductive material such as polyvinyl chloride. The gas line should be installed in a separate trench from the electrical grounding components to prevent potential interference. The type of conduit used for electrical and gas lines is also important. High-density polyethylene conduit is a suitable option for both electrical and gas lines. However, it is important to ensure that the conduit is properly sized for the application. The conduit should be large enough to accommodate the wires or pipes that will be installed inside it. The conduit should also be rated for the appropriate voltage and temperature. The National Electrical Code, or NEC, provides comprehensive guidelines for electrical installations, including grounding and bonding requirements. Grounding refers to the intentional connection of a neutral conductor or equipment chassis to earth, establishing a zero voltage reference point and facilitating the safe dissipation of fault currents. Bonding, on the other hand, involves connecting metallic parts of an electrical system to create an electrically conductive path, ensuring that all bonded components are at the same potential. Article 250 of the NEC is dedicated to grounding and bonding, outlining specific requirements for various electrical systems and equipment. This article covers topics such as grounding electrode systems, grounding conductors, bonding jumpers, and equipment grounding. Section 250.4 provides general requirements for grounding and bonding, emphasizing the importance of creating a low impedance path for fault current to return to the source. This section also highlights the need to minimize voltage gradients and prevent electrical shock hazards. Section 250.50 outlines the requirements for grounding electrode systems, specifying the types of electrodes that are permitted and the methods for installing them. Permitted grounding electrodes include ground rods, metal underground water pipes, and concrete encased electrodes. This section also addresses the use of multiple grounding electrodes and the requirements for bonding them together. Section 250.66 provides guidance on sizing grounding electrode conductors, which are used to connect the grounding electrode to the electrical system. The size of the grounding electrode conductor is based on the size of the service entrance conductors. Section 250.92 outlines the requirements for bonding service equipment, such as service panels and meter enclosures. This section emphasizes the need to ensure that all metallic parts of the service equipment are effectively bonded together. Section 250.118 specifies the types of equipment grounding conductors that are permitted. Equipment grounding conductors are used to connect the non-current carrying metal parts of equipment to the grounding system. Permitted equipment grounding conductors include copper conductors, aluminum conductors, and rigid metal conduit. In addition to Article 250, other articles of the NEC also address grounding and bonding requirements for specific types of equipment and systems. For example, Article 430 covers grounding requirements for motors and motor controllers. Article 500 through 516 cover hazardous locations. Article 680 covers grounding requirements for swimming pools and spas. Understanding and complying with the grounding and bonding requirements of the NEC is essential for ensuring the safety and reliability of electrical installations. Improper grounding and bonding can lead to electrical shock hazards, equipment damage, and fire. Therefore, it is important to consult with a qualified electrician or electrical engineer to ensure that the grounding and bonding system is properly designed and installed. When working with underground utilities, safety is paramount. Before any excavation begins, it is essential to contact the local one-call center to have underground utilities located and marked. This will help to prevent accidental damage to underground utilities, which can result in serious injuries or property damage. During excavation, it is important to dig carefully and avoid using heavy equipment near underground utilities. Hand digging may be necessary in the vicinity of underground utilities. If an underground utility is damaged, it is important to report the damage immediately to the utility company and the local authorities. Do not attempt to repair the damage yourself. Stay away from the damaged utility and warn others of the potential hazard. In addition to following safe excavation practices, it is also important to wear appropriate personal protective equipment, or PPE. PPE includes items such as hard hats, safety glasses, and gloves. Hard hats protect the head from falling objects. Safety glasses protect the eyes from flying debris. Gloves protect the hands from cuts and abrasions. It is also important to be aware of the potential hazards associated with working in trenches. Trenches can collapse, trapping workers inside. To prevent trench collapses, it is important to slope the sides of the trench or use shoring to support the trench walls. A competent person should inspect the trench daily to ensure that it is safe to work in. When working with electrical equipment, it is important to follow lockout-tagout procedures. Lockout-tagout procedures are used to prevent accidental energization of electrical equipment during maintenance or repair. Lockout-tagout procedures involve disconnecting the electrical equipment from its power source and placing a lock and tag on the disconnect switch. The lock and tag prevent the switch from being turned on accidentally. Only the person who placed the lock and tag on the switch is authorized to remove it. In addition to following lockout-tagout procedures, it is also important to use insulated tools when working with electrical equipment. Insulated tools protect the worker from electrical shock. The tools should be rated for the voltage of the electrical equipment being worked on. It is also important to avoid working in wet conditions. Water can conduct electricity, increasing the risk of electrical shock. If it is necessary to work in wet conditions, use waterproof clothing and gloves. In conclusion, safety should be the top priority when working with underground utilities and electrical equipment. By following safe excavation practices, wearing appropriate PPE, following lockout-takeout procedures, and using insulated tools, workers can minimize the risk of injuries and accidents. Remember to always consult with qualified professionals and adhere to local regulations and codes to ensure a safe and compliant working environment.